I was resizing a logo the other day, and I was just struck by something.
Oh, yeah. What was that?
I was blowing it up from this tiny little icon to the size of a movie poster, and the lines just remained, well, flawless.
Perfectly crisp and smooth.
Exactly. And it got me thinking, have you ever wondered what invisible math makes that kind of thing possible? That sort of effortless elegance.
It feels completely intuitive when we see it, right?
Yeah.
But that effortless motion, that precision, it's all built on some really foundational geometry.
Okay, let's unpack that.
Yeah.
Today we are doing a deep dive into Bézier curves, the fundamental mechanism behind pretty much every smooth digital curve you see.
From fonts to factory robots, yeah. And the story really starts with industrial efficiency.
Right, they're named after Pierre Bézier, the French engineer at Renault.
Exactly. He used them in the 1960s to design the sleek bodywork for their cars. But what's really fascinating is that the mathematical recipe for them goes way back.
How far back?
To 1912. A mathematician named Sergei Bernstein developed the underlying polynomials.
So the math was sitting there for decades. But I think there was another name in the mix, right? Someone at Citroën?
Yes, Paul de Casteljau. Working completely independently in 1959, he developed the actual algorithm we use to calculate points on the curve.
So two rival French car companies basically gave us the engine for all modern vector graphics.
A pretty amazing piece of simultaneous invention.
It is. So for anyone listening, how does this actually work? What defines a Bézier curve?
Well, the core concept is really about simplicity through indirect control.
Indirect control.
A curve is defined by a set of discrete control points. Let's call them P0 through Pn.
Right.
And here's the crucial part. The curve always, and I mean always, starts at that first point, P0.
And it has to end exactly on the last one, Pn.
Precisely. That's called the endpoint interpolation property.
So we've locked in the start and the end. But what about the points in the middle? Like in a cubic curve, which is super common, you have 4 points. The two in the middle don't even touch the curve.
And that's the genius of it. If the curve had to pass through every single point, you'd get these weird wiggles or sharp corners.
I see.
Instead, those intermediate points, P1 and P2, they act more like magnets or directional handles. They pull the curve.
So they're defining the direction the curve takes as it leaves the start and approaches the end.
Exactly. The farther you pull those handles away from the endpoints, the more aggressively the curve has to bend to follow them. You're basically increasing the tension.
So if I move P1 farther away from P0, I'm creating a stronger pull, making the arc wider.
You've got it. It gives you these incredibly smooth, predictable adjustments.
I know cubic curves are the standard in vector graphics, like in SVGs. But what about quadratic curves? They only need 3 points.
And they're great. They define a perfect parabolic arc. You actually see them a lot in true type fonts.
So why did the industry settle on cubic for most design work?
It's just the perfect balance. A cubic curve gives you 2 separate handles to control the entry and exit directions independently. That lets you model almost any complex shape you need while still being really, really fast to compute.
And that speed comes back to de Casteljau's algorithm, right? The engine room.
It does. His algorithm is it's a beautiful recursive process.
Can you break that down a bit?
Sure. Imagine you connect your 4 control points with straight lines. The algorithm just finds a point along each of those lines, connects those new points, and does it again.
So it keeps shrinking the set of lines?
Over and over, until you're left with a single point that lies perfectly on the final smooth curve. It's incredibly stable with no numerical errors.
That kind of predictable stability. Finding the most efficient path forward. Speaking of intelligent design and stability, this deep dive is sponsored by Embersilk. If you need efficiency or a clear path forward, like figuring out where AI agents could make the most impact for your business, check out embersilk.com for AI training, automation, and iteration.
And that mathematical precision, it translates directly into the physical world, too. Think about animation.
Easing, right.
Easing, exactly. Bezier curves define velocity over time, that acceleration and deceleration. It's what makes digital movement feel like it has actual weight in physics.
And it all comes full circle back to the car engineers. These curves are still defining motion in manufacturing.
Absolutely. Modern robotics depends on them. A welding arm on a factory floor needs a perfectly smooth trajectory, no sharp turns.
Because that would cause unnecessary wear and tear.
And waste energy. By using these curves, they get extreme precision and efficiency, task after task.
It's just so inspiring. These simple geometric ideas, perfected decades ago for a car bumper, are now driving the elegance of motion in everything.
It's a great reminder that these fundamental breakthroughs in math just keep opening up new possibilities for a more efficient and, honestly, a more beautiful future.
So next time you see a perfect curve or a smooth animation, you can think of those hidden control points pulling the strings.
The invisible architecture of elegance.
If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.